Welcome to Session 6 of Unit 1 in learning the course Design and Analysis of Algorithms. In our previous sessions, we discussed about what is algorithm, what are the characteristics of algorithm, and how to specify an algorithm. Also, we discussed about performance analysis and asymptotic notations. Also, we seen randomized algorithms. In our today's session, we are going to learn about disjoint sets and disjoint set operations. The main objectives of this session are to know what is a disjoint set, to learn and implement various disjoint set operations. The learning outcomes of this session are, by listening this session, one can understand what are disjoint sets and able to implement disjoint set operations. The main topics that we are going to discuss in this session are what is disjoint set, operations on disjoint sets. Mainly we focus on union, find, weighted union and collapsing find operations. Coming to disjoint set, what is a disjoint set? Or what are disjoint sets? Two sets are said to be disjoint sets if they have no element in common. What are disjoint sets? Two sets are said to be disjoint sets if they have no element in common. That is, the two sets must have distinct elements. The elements in two sets must be distinct. Or we can say that two sets are disjoint sets whose intersection is an empty set. If you perform intersection between those two sets, if the result is an empty set, then we can say those two sets as disjoint sets. Suppose, for example, consider a set S is equal to 1, 2, 3, so on 10. That is, this set S is having 10 elements. Now, I am going to partition this set S into 3 disjoint sets. Let us see. I have taken S1 is equal to 1, 7, 8, 9, S2 is equal to 2, 5, 10, and S3 is equal to 3, 4, 6. If you observe these three sets, the intersection of S1 and S2 is an empty set. There is no any common element between these two sets. And also the intersection of S2 and S3, this is also an empty set. And the intersection of S1 and S3, this is also an empty set. So these three sets are said to be disjoint sets. These three sets are said to be disjoint sets. How to represent disjoint sets? The possible representation for disjoint sets is a tree-like structure. Let us see the tree-like structure. The set S1 is represented like this. Here I have considered 1 as the root node and 7, 8, 9 as the child nodes. Always you have to remember that in the representation of sets, the arc is pointed towards root node. Arc must be pointed towards root node. Here if you observe, every arc here I pointed towards root node. If you observe, this represent set 2. Here I considered 5 as the root node, 2 and 1 are the child nodes. If you observe set 3, here 3 is the root node, 4 and 6 are the child nodes. If you observe all the three disjoint sets, in all the three disjoint sets, I represented the arc towards root node. But in general trees, there may be directions or there may not be directions. But here, the arc should be represented as directed and it always pointed towards root node. Next. Coming to operations of disjoint sets, we have basically two operations. One is union and another one is find. Union and find. Coming to union operation. What is union operation? If Si and Sj are two disjoint sets, if Si and Sj are two disjoint sets, then their union can be represented as Si union Sj. if Si and Sj are two disjoint sets, then their union can be represented as Si union Sj. And how to define that union? Si union Sj contains an element X such that X is in a Si or X is in Sj. The X may be present in Si or the X may be present in Sj. That is, for example, let us consider Si contains the elements 1, 2, 3 and Sj contains the elements 5, 7, 8. The union of Si and Sj can be represented as Si union Sj is equal to 1, 2, 3, 5, 7, 8. 1, 2, 3, 5, 7, 8. That is, it is a combination of elements which are present in both Si and Sj. Now, coming to find of I. Given the element I, find the root node of the set containing I. That is, here find of I, the operation find of I finds the root node of the set in which the element I is present. The root node of the set in which element I is present. That is, for example, here I am representing the set Si as like this. What the example that we have taken earlier, I am representing the set Si as like this, and I have represented the set Sj as like this. And by uniting these two sets, either 1 may become the root node or 7 may become the root node. I am making 1 as the root node. So here I can represent the union of Si and Sj as like this. Like this. Now, suppose for example, if I have given find of 8. If I have given find of 8, that is I is 8. What that find operation returns? This find operation returns the root node of the set in which the element 8 is present. Here, this is the set. On this set, I want to implement find of 8. Now, here, in which set this 8 is present? In this set the 8 is present. What is the root node of 8? 1 is the root node of 8. So here you observe that 7 is the parent of 8. But 7 is not the root node. 1 is the root node. So find of 8 is equal to 1 in case of this set. So here find operation finds the root node of the set in which the element I is present. Now I am going to explain the algorithms for simple union and simple find. Let us see, this gives the algorithm for simple union. Algorithm union of I comma j. Here what is that I, j? I and j are the root nodes of the sets in which the elements I and j are present. I is the root node of the set in which the element I is present, and j is the root node of the set in which the element j is present. Now union operation does either parent of j is equal to I or parent of I is equal to j. Parent of j is equal to I or parent of I is equal to j. In any case, we can implement any of those two. Any of those two we can implement. We can make I as the parent of j, or we can make j as the parent of I. Now I am going to explain this with some simple example. Let us see. Here I have taken S1 is equal to 1, 2, 3, 7 and S2 is equal to 5, 8, 9, 6. Now here the S1 can be represented as a tree. Here for this I have represented 2 as the root node and 1 becomes the child node, and 3 also a child node, 7 also a child node, and S2 is represented as 6 is the root node, 5 is a child node, and 8 is a child node, and 9 is a child node. If I represented S1 as like this and S2 is like this, now I want to implement union of 2, 6. union of 2 comma 6. That is I is equal to 2 and j is equal to 6. Here I is equal to 2, j is equal to 6. What simple union operation tells us? Make parent of j is equal to I or parent of I is equal to j. We need to make either I as parent of j or j as parent of I. Now if I taken this one, I'm making j as I as parent of j, that is parent of 6 is equal to 2. Parent of 6 is equal to 2. So by making parent of 6 as 2, I can write 6 parent is 2. Then the relation between those two becomes like this. The remaining elements can be represented as it is. So the union of these two can be written as like this. The union of these two can be written as like this. This gives the union operation between the sets S1 and S2. So if you implement this, if you implemented this one, what becomes the union? Here 6 becomes the parent and 2 becomes the child. Remaining elements can be written as it is. We can implement either this or this. This gives simple union operation, right? I'm going to explain you simple find. This is one more example which explains about the union operation. Now here initially I have taken 6 sets which are containing 6 individual elements. One is the element which is present in the first set, 2 is the element which is present in the second set. Like that I have taken 6 sets. After performing union of 1 comma 3, I can make parent of 3 as 1 or parent of 1 as 3. Now here I made parent of 3 as 1. You can observe here the parent of 3 becomes 1. Now I am performing another serial operation on these sets, union of 2 comma 5. Now I made parent of 5 as 2. You can observe here parent of 5 is 2. Now I made another union operation on those sets, union of 1 comma 2. Here I made parent of 2 as 1. Here you can observe parent of 2 is 1. Now if I represented the tree structure for all these union operations, I'll get 1 is the root node, the child of 1 is 2. Since parent of 2 is 1, I represented 2 as the child. In the same way, parent of 3 is 1, I represented 3 as child, and also parent of 5 is 2, I represented 5 as child of 2. So the 3 union operations can be represented by using this type of tree structure. This is one more example for union operation. Now let us see another one more important concept in case of union operation, which is nothing but the union operations. If you perform the union operations in a sequential manner, that is union of 1 2, union of 2 3, union of 3 4, union of 4 5, union of 5 6, and so on, union of n minus 2 n minus 1, union of n minus 1 n. If you perform all these union operations in a sequential manner, so how you can do that? So first let us see, if I perform union of 1 comma 2, union of 1 comma 2, I can made 2 as parent of 1, 2 as parent of 1. If I perform union of 2 3, I can made 3 as parent of 2. I can, if I perform union of 3 4, I can do 4 as parent of 3. In the same way, if I perform the sequence of operations, I can made n as parent of n minus 1, n as parent of n minus 1. So here this type of tree structure which is obtained by the sequence of union operations of n elements is called as a degenerate tree. It is called as a degenerate tree. Here you can see this tree. 1, its parent is 2, and so on. If you perform like this, n minus 1, its parent is n. So here this tree structure is called as a degenerate tree. Right. Next. Next we are going to see find operation. I already said you that what is find operation? Find operation determines the root of the tree containing the element I. It finds the root of the tree which contains element I. Now what is algorithm for find operation? Let us see the algorithm. Algorithm find of I. Here I is an element which is present in a tree structure or in a set. Here we are going to find the root node where this particular element I is present. Now I taken or I assigned I value to j, while p of j greater than 0, what I am doing? J is equal to p of j, and finally if the condition is false, I am going to return j. What I am doing here? I am going to find the parent for every element. In the different levels, I am going to find the parent. Finally, I will return root node. Okay, now I am going to explain this with an example. Let us see the example. Here, I have a set S is equal to 3, 4, 5, 7, 9, 6. So, whose tree structure is 7, 5, 4, 6, 3, 9. Suppose let us consider the tree structure for the given set is like this. Now I want to do find of 3. Find of 3. Let us see how to do find of 3. Here I is equal to 3. According to the algorithm, what I am doing? J is equal to I. That is J is equal to 3. I assigned I value to J. Now what I am doing? While P of J greater than 0, what I am doing? J is equal to P of J. What I am doing? Let us see the previous slide. Here while P of J greater than 0, J is equal to P of J. So, while P of J greater than 0, J is equal to P of J. Now, let us see P of J, that is parent of 3 greater than 0 or not. Whether the condition is true or not, I am checking. Parent of 3. What is parent of 3? 6 greater than 0. Yes, condition is true. Since the condition is true, I am making 6 is equal to, J is equal to parent of J, that is parent of 3, which is nothing but 6. Now, the condition is not false. Again, we need to check the condition. Again, I am going to check the condition. P of 6 greater than 0 or not. What is parent of 6? Parent of 6 is 7. It is greater than 0. Again, condition is true. So, I made J as 7. Again, the condition not false. Again, we need to check the condition. Now, I am checking the condition. P of 7 greater than 0 or not. What is P of 7? There is no parent for 7. So, we can take it as -1, which is greater than 0. Condition is false. So, we can come out of the loop. We can return J. What is the latest value for J? 7. That is returned. Return 7. So, find operation finds the root node of the tree in which the element 3 is present. Here, whether 7 is root node or not for this tree? Yes, obviously 7 is the root node for the tree in which that element 3 is present. So, here this find operation returns the root node of the set in which the element I is present. So, find of 3 is 7, right? Next, here this is one more example for find operation. Here find of 5. What is find of 5? It should be 1. Find of 5 is not equal to 2. 2 is the parent of 5, but 2 is not the root of 5. Here the root of 5 is 1. So, find of 5 is equal to 1. Find of 2. Find of 2 is also 1. Find of 3 is also 1. This is one more example for that find operation. Let us see weighing rule for union, which is an extension for simple union. So here, what is weighing rule? In our previous case, in simple union operation, we are making, if you want to unite two sets whose root nodes are I and j, what I am doing? I am making either parent of I as j or parent of j as I. We are not sticking to any one. We can do anything. I can make I as parent of j, or I can make j as parent of I. So we have a confusion there. What we need to do? Whether I have to make I as parent or I have to make j as parent. So we have a confusion there. So to avoid that confusion, we have this weighing union. What is this weighing union or weighed union? What is this weighing rule for union? So the union operation which follows weighing rule is called as weighed union operation. The union operation which follows weighing rule is called as weighed union. Now what is weighing rule? Here let us see the weighing rule. Weighing rule for union of I comma j. If the number of nodes in the tree I is less than the number of nodes in the tree j, then make j as parent of I. Otherwise make I as parent of j. That is, the nodes in the tree I is less than the nodes in the tree j, then we are making j as parent. That is, I is root node of one tree, j is root node of another tree. I am finding the number of nodes in this particular tree where I is parent, and I am finding the number of nodes in the tree where j is parent. If the number of nodes in the first tree is less than the number of nodes in second tree, then we are making j as parent of I. That is simply saying which set is having more element. Which set is having more elements, its root becomes the root of union. Its root becomes the root of union. In which set more elements are present, that itself is to be considered as the root of union operation. Okay, now let us see the weighed union algorithm. Here I want to do the union of the two sets whose root nodes are I and j. Here first I am finding x is equal to minus count of I and y is equal to minus count of j. Here count is a function which is used to count the number of nodes that are present in that particular tree. And z is equal to x plus y. If x is greater than y, parent of I is equal to j, count of j is equal to minus z. Else, if this condition is false, in that case, parent of j is equal to I, count of I is equal to minus z. Now, let us see, I am going to explain this with an example. So, here I want to perform the union of two sets. Here S1 is 1, 2, 3, S2 is 4, 5, 6, and here I represented S1 as like this and S2 as like this. Now for our convenience, here I have taken one more element in S2, 7. So okay, S1 contains 3 elements and S2 contains 4 elements. Now I am going to apply weighed union on these sets. Now what we need to do? What is the first step in weighed union? Let us see. X is equal to minus count of I, y is equal to minus count of j. Let us see. Here union of I comma j, 2 comma 5. Union of 2 comma 5. Here I is 2 and j is 5. Now here what I am doing? X is equal to minus count of I, that is which is equal to minus 3. Here what is count of I? Which contains 3 elements, so minus 3. Now y is equal to minus count of j. Here this is minus 4 which contains 4 elements, so minus 4. Z is equal to x plus y which is equal to minus 7. Z is equal to minus 7. Now what is the next step that we are doing in the algorithm? Let us see. If x greater than y, parent of I is equal to j and count of j is equal to minus z. If x greater than y, if x, what is x value? Minus 3 greater than minus 4. If x greater than y, then make parent of I is equal to j. Here, whether this condition is true or not, yes, this condition is true. -3 is greater than -4. So, what we need to do? Parent of I. What is I? 2. Parent of 2 is equal to, what is j? 5. Parent of 2 is equal to 5. Then, here, z value becomes, here, count of I, that is count of 2 is equal to z minus of -7, which is equal to 7. Now in this case, the union operation can be represented as 5 becomes root node and these 3 childs are 4, 6 and 7, and 2 also becomes a child of 5. So this becomes the Wade union result on those two sets. I hope you all understood the Wade union operation. Next we are going to see example for one more example for Wade union. Let us see. Here I have already all individual elements 1, 2, so on, n. Now in the first case we are implementing union of 1, 2. 1 contains a single element, 2 contains a single element. So in this case both are having same number of elements, 1 element. So in this case we can make either 1 as parent or 2 as parent. Since first element is 1, I made 1 as parent. After that I want to do union of 1, 3. In this case, this first set contains 2 elements and this set contains 1 element. Then which becomes parent? In which more number of elements are present, that becomes parent. So 1 becomes parent. So since 1 becomes parent, 3 becomes child. Now if you implement this in this way, the sequence of operations, finally if you do union of n, the first set which is having the elements 1, 2, 3, so on, n minus 1, and here we have n. Now if you unite these two, in this case since this is having more number of elements, 1 becomes the parent of n. So the final set is like this. The final set is like this. Now next see collapsing find operation. What is collapsing find operation? The find operation which obeys collapsing rule is called as collapsing find. The find operation which obeys collapsing rule is called as collapsing find. What is that collapsing rule? Let us see the collapsing rule. If j is a node on the path from I to its root, then set parent of j is equal to root of I. Here what is collapsing rule? If j is a node on the path from I to its root. Suppose for example I is a node and here its root node is present, and in between this there are a number of nodes are attached, and here j is another node. Like this the tree is present. So j is a node which is present in the path from I to its root. Here its root is R. J is a node which is present in the path. In this case, according to collapsing rule, what I need to do? I need to make R as parent of J. R as parent of J. Here we need to do this one. The parent of J is R. Root node becomes the parent of J. Parent of J is equal to root of I. Here root of I is R. So parent of J becomes R. So like this we need to do. Okay, let us see the algorithm for collapsing find. Find the root of the tree containing element I. Use the collapsing rule to all nodes to collapse from I to the root R. Here I take an R is equal to I. While P of R greater than 0, do R is equal to P of R. In this step, what I am doing is I am going to find the root of R. I am going to find the root of R. While I not equal to R, while I not equal to R, I am doing T is equal to P of I is equal to R, I is equal to T. That is, I am making the root as parent of intermediate node. Root as parent of intermediate node. And finally, I am returning R. Finally, I am returning R. I will explain you this with an example. Let us see the example. Here, I have taken a set S which contains the elements 3, 4, 2, 7, 6, whose tree structure is represented as like this. Here, the tree structure for this set is represented as like this. Now, in this case, I want to do find of 6. I want to do find of 6. Now, what we need to do according to the algorithm? What is the first step in algorithm? R is equal to I. While P of R greater than 0, R is equal to P of R. R is equal to I. Now here R is equal to, here I is 6. So I made 6. I assigned I value to R. Now what is the next step? While P of R greater than 0, R is equal to P of R. We need to do R is equal to P of R. Let us see the statement. P of 6 is equal to, what is P of 6? 4. Greater than 0 or not? Yes, condition true. So R becomes P of R, that is P of 6, which is nothing but 4. Now again the condition is not false, so we need to check the condition again. So P of 4, what is P of 4? 2, greater than 0. Yes, condition is true, so R becomes 2. Again the condition is not false. P of 2, which is minus 1, which is greater than 0, condition is false. We are coming out. So the final R value is 2. Okay, now the next step, what we need to do, the next step, while I not equal to R, while I not equal to R, what we need to do? T equal to P of I is equal to R, I is equal to T. Here, what is the next one? While I not equal to R, T is equal to P of I is equal to R is equal to T. Is it? Let us see once again, let us see. T equal to P of I is equal to R, I is equal to T. T is equal to P of I is equal to R is equal to T. Let us see. While I, what is I? 6, not equal to 2. Yes, condition is true. 6 not equal to 2. So T is equal to P of I, that is P of 6. What is P of 6? 4. And P of 6 is equal to R. What is R? 2. R is equal to T, which is 4. Again the condition we need to check. 4. Here I value is 4. Here the last step is I is equal to T. So here I is equal to 4. 4 not equal to 2. Again the condition is true. So T is equal to P of I, that is P of 4. What is P of 4? 2. Now P of I is equal to, that is P of 4 is equal to R, which is R2, and I is equal to T. What is T? 2. Now again I am going to check the condition. 2 not equal to 2. Here condition becomes false. Condition becomes false. What I need to return? Finally I need to return R. So here I returned R. Return R. What is R? R value is 2. Okay, now let us observe the intermediate cases. I made P of 4 is 2 as well as P of 6 is also 2. By implementing this operation, the above tree is converted as 2, 3, 4, and I need to make the parent of 6 as 2. So here this is 6, and in this case the parent of 7 becomes 4. The tree is converted as like this. The tree is converted as like this. So this gives the collapsing find operation. This gives collapsing find operation. Next, this gives another example for collapsing find operation. Here, find of 5. Since the root node of 5 is 0, here I am making the 0 as parent of 5. 0 as parent of 5. So I hope you all understood what the concepts that we explained in this session. I'm going to summarize the concepts what we explained in our today's session. In today's session, we explained about what are disjoint sets, how to represent disjoint sets, what are disjoint sets. The two sets are said to be disjoint if their intersection is a empty set, if their intersection is an empty set. And how to represent disjoint sets? By using a tree-like structure. That is, the arc should be pointed towards root node. And also we discussed about operations of disjoint sets. We seen union operation, find operation, and also we explained about Wade union and collapsing find operations. For explaining about that Wade union and collapsing find, we also explained about weighing rule for union and collapsing rule for find operations. I explained all these various algorithms with examples. To assess yourself, I given some questions. Let us answer these questions and send me answers. The first question is, a disjoint set can be defined as option A, the sets whose union is an empty set. Option B, the sets whose intersection is an empty set. Option C, the sets whose difference is an empty set. Option D, none of the above. The next question is, implement Wade union operation on the following sets. Here I have given 3 sets. Here I have given 3 sets. Implement Wade union operation on those 3 sets and implement collapsing find operation on the set obtained by implementing the above operation. So if you implement Wade union operation on these sets, you will get a set, one set. On that set, you need to implement find of 2. You need to implement find of 2. So please prepare answers for these questions and share me answers through the given mail. Here, in preparing this presentation, I used the digital content from various public sources. I am using this presentation only for educational purpose, not for any commercial purposes. Thank you for listening the session.